So, if you haven't signed in, please sign in with the sign-in sheet. Let me make sure this hides itself. And we will be starting astronomy today. Especially if you weren't here last time, make sure you sign in. Because if you miss the first 2 days, you're gonna get automatically dropped. As a no-show. So I'm gonna get started. So let's start talking about the origin of modern astronomy. So we'll start by looking at some of the history of astronomy. We'll look at the geocentric view of the solar system, which is the ancient view of the solar system, and how it differs from the modern heliocentric view. We'll list and describe the contributions to modern astronomy of Nicholas Copernicus, Tycho Brahe, Johannes Kepler, Galileo Galilei, and finally Isaac Newton. We'll talk about how constellations are used in modern astronomy. Please sign in. We'll describe the 2 primary motions of Earth and explain the difference between a solar day and a sidereal day. We'll look at the changing configuration of the Earth-Moon system that produces the regular cycle we call the phases of the moon. And we'll go over how the configuration of the Earth-Moon-Sun system produces eclipses, lunar eclipses and solar eclipses, and which configuration produces each. So, ancient astronomy started because people looked at the sky, and looking at the sky turned out to be useful. So early civilizations kept records of the positions of various celestial objects, believing they were either good or bad omens, but additionally they were useful for navigation and calendars. There's evidence of very old records of people recording moon phases, probably for calendar purposes. So this was groups like the Chinese, the Egyptians, the Babylonians. They all recorded and studied the sky. Now, the golden age of astronomy was in Greece from around 600 BCE to around 150 CE. So this used observational data as well as geometry and trigonometry to create detailed models of the universe and also start to collect a lot of the data from earlier studies. Now, the ancient Greeks, most ancient Greeks held a geocentric or Earth-centered view of the universe. This makes sense. If you're living on Earth, it looks like, and you look at the sky, it appears that everything is orbiting the Earth, not something different like the Earth is orbiting the sun or some strange thing like that. There's no obvious indications of this. So the original the concepts the Greeks had were things like that the Earth was a motionless sphere at the center of the universe, and stars were on the celestial sphere, which was this transparent hollow sphere that rotated daily around the Earth. And this is what it looks like from the ground. So here are some of the things that were discovered. Aristotle was able to determine that the Earth had to be a sphere because he studied the shadows that the Earth made on the moon during a lunar eclipse, and they were round. So, the Earth makes a curved shadow when it eclipses the moon, and the only thing that could really do that would be a ball. Eratosthenes calculated Earth's circumference to within 500 miles of the current measurement using the angle of the noonday sun in 2 different locations. And 2 different cities in Egypt. So a lot of this actually happened in like Alexandria and Greek Egypt. Aristarchus was one of the first to propose a heliocentric or sun-centered universe due to the geometry of moon, earth, sun relationships, but didn't really have any support for it, and also proposed a whole bunch of other weird stuff. Hipparchus mapped stars and calculated a year to within minutes of modern measurements. He made a map of the stars in the sky. He cataloged the stars in the sky, and he was also able to determine the precession of the Earth. So the Earth, it rotates, but it also wobbles like a top. And he was able to determine the rate of precession of the Earth, which is how the pole star, the North Star, seems to move. So here is a short video about how Eratosthenes was able to calculate the circumference of the Earth using the shadow of the noonday sun on a specific day at two places.
Hello and welcome back for another Smart Figure. This is Callan Bentley, and today we're going to take a look at an amazing calculation that was done over 2,000 years ago to figure out the size of planet Earth. This was done by the natural historian Eratosthenes. Eratosthenes knew that at the city of Syene, what today we call Aswan in Egypt, that there was a well and that sunlight reached the bottom of that well on a certain day of the year. Eratosthenes figured that if he compared that to the orientation of the sunlight at a different site, he could use that information to calculate the size of the Earth. The specific place that he chose as his second site was the city of Alexandria, also in Egypt, and more or less north of Syene. Here is his logic. If the sun's rays are coming in and going exactly down that well at Syene, then they're going to intersect a vertical obstacle, such as an obelisk or a post at Alexandria, at an angle that's not exactly parallel. So in other words, that post will cast a shadow, and that shadow's length will be a function of the height of the post and then the angle of the sun's rays. So the post is vertical, and so if you continue that line straight down, you get to the center of the Earth, and the well at Syene was also vertical. So there's going to be a triangle that gets drawn here. On this given day of the year, when the sunlight came exactly down the well, Eratosthenes had a colleague measure the length of the shadow at the post in Alexandria. And it turns out that that shadow was coming off the post at a 7-degree angle. Well, if that angle is 7 degrees, then this angle is also 7 degrees. 7 degrees is 1/50th of a circle. So Eratosthenes reckoned that the distance between the post at Alexandria and the well at Syene was 1/50th the circumference of the Earth. He measured that distance, and that distance was 5,000 stadia. The stadium was a unit of measurement back in those days. Don't worry for the moment how long an individual stadium is or how long 5,000 stadia are. For the moment, let's just go ahead and follow Eratosthenes' calculation. So if there's 5,000 stadia between these two cities, and the angle between a line connecting the center of the Earth with Alexandria and a line connecting the center of the Earth with Syene was 7 degrees, then basically we need to multiply 5,000 stadia times 50. 7 degrees is 1/50th of a full circle. So that number comes out to 250,000 stadia. The best historical estimates are that a stadium is about 157.6 meters, and so therefore it's 0.1576 kilometers. So if you do the math there, you come up with an estimate of 39,400 kilometers. So if you want to express Eratosthenes' estimate of the Earth's circumference in modern day units, it would be 39,400 kilometers. Now, we've got other methods of measuring Earth's circumference today, and we can compare them to Eratosthenes' estimate. The modern day estimate is around 40,075 kilometers. So if you compare Eratosthenes' estimate to the modern estimate, he got it 98.3% right. That's pretty good considering all he had to work with was a well, a post, and a good sense of geometry. Thanks a lot for your attention. This has been another Smart Figure.
He was able to make some very impressive calculations. Now, the ancient Greeks, when they described what they saw in the sky, they observed there were all these stars that didn't move relative to each other. And then there were 7 objects that appeared to move across the background of stars. These objects were wanderers or planeti, hence where we get the word planet. These changed position in the sky. These were 7 wanderers. These were the Sun, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn. And in many languages, those are what the days of the week are named after. Not so much in English, but some of them are still, Sunday, Monday, but Saturday. Now, in 141 CE, Ptolemy, who was a mathematician living in Alexandria, was able to put together a model of the universe that was able to make truly excellent predictions of where planets would be located. He published it in this book called the Almagest. This was a geocentric model. So the problem with the planets, so the sun and the moon aren't hard to predict. You could guess where they're going to be pretty easily. They move in a reasonable sort of manner continuously around the Earth across the background of the stars. But the planets do this weird thing where every once in a while, so the planets will get bigger and smaller, and every once in a while they'll slow down or speed up, and sometimes they'll slow down and even turn around and go backwards, go the opposite direction to where they would do the direction they would normally go. Yeah. And that was hard to explain. There wasn't a good, simple explanation. It didn't fit with the models of the universe people had, where the heavens were perfect and everything was spinning around in perfect circles at constant velocity, because that was, what perfect things did. So to explain the fact that planets appear to come to a stop and go backwards sometimes, Ptolemy had to make a more complicated model. He used 2 motions for the planets. You had large orbital circles that were called deferents, and going around these deferents would be smaller circles called epicycles, and the planets would be going around on the epicycles. So he did circles on circles. And well, this is correct. It was actually able to make excellent predictions. Turns out circles on circles is a really pretty good way to approximate the actual motion of planets. And in theory, with enough circles on circles, you can generate any motion. So that will eventually work. But this model, it's incorrect, but it predicted motions with accuracy for a century. It was able to predict like a century in advance. It was a very good model. But over time, people started to realize there were some issues with it. And it just wasn't really satisfying that you had to use circles on circles to explain motion. So this is sort of an example of the universe according to Ptolemy. The Earth is at the center. All the planets are on small things that rotate around as they travel around. The moon and the sun orbit the Earth. So that's sort of Ptolemy's model. Circles on circles. So here is a video explaining how retrograde motion is explained in the Ptolemaic system and in the modern heliocentric system. So the different, how you use epicycles to explain retrograde motion and how you can use heliocentrism to explain retrograde motion.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the ancient Ptolemaic way of explaining retrograde motion of the planets by use of epicycles. So we all know what our solar system looks like. I think we all have a cartoon picture of the solar system in our heads. And of course, it includes the sun, and it includes the Earth, and it includes a bunch of other planets as well. If you look up in the night sky, at a glance, a planet might look a lot just like a star, like a bright star perhaps, or a slightly reddish star, but there's not much to distinguish them from stars at first glance. It's only when you watch them over successive nights that you realize that the planets move against the background of stars. And in fact, this is where the name planet comes from. It basically means wanderer. So these certain celestial objects were wandering across the night sky. An example of this is shown here in this image. We've got Earth over on the left, and then the apparent path that Mars takes as seen against background stars. So it looks like Mars is moving along to the east most of the time, but then for part of the cycle, Mars moves back towards the west, and then it moves on towards the east again. So this was an odd sort of behavior, and it didn't really jive very well with the ancient notion that a circle is sort of perfect, and therefore anything that's up in the heavens must be perfect, and therefore it must be moving in a circular motion. So one way to reconcile this odd motion with this idea of the perfect circle, and of course the Earth at the center of the universe, is the idea that's illustrated here in this picture, that each of the planets had an orbit. This orbit is sometimes called a deferent, and then in addition to that orbit, there was an additional circular motion, which is called an epicycle. Epicycles are here, deferents are here, and you can see how, for instance, Saturn has this deferent, and then it has this epicycle. So when you put those two together, it can explain that retrograde motion. At least that was the idea. How does that actually work? Well, you've got the two circles seen over here on the left, and you can see how the planet is moving along the epicycle in addition to moving along its deferent. And that produces an overall motion for that planet like is shown over on the right side of this figure. So if we go ahead and let that planet start moving along its path, you can see that it is going to take this odd path that is somewhat like the path of your pen when you use a spirograph design drawing toy. And you can see that it's moving closer to the Earth at some points, and it's moving further away from the Earth. But during that little bit that it just did there, it went through retrograde motion. And then it moves back out into the outer part of both the epicycle and the orbit, and that explains that retrograde motion. So that basically gives us a pattern for what the universe looks like that is rather more complex perhaps than it needs to be, but it's a pretty good model for the solar system if you accept the premise that Earth is at the center of the solar system. And of course we have very good evidence that Earth is not at the center of the solar system. In fact, the sun is at the center of our solar system, and as for the universe itself, it's way more complicated still. So that brings us back to this image here. We are looking at the apparent path of Mars seen against the background stars, but that's not Mars's actual path. We know today that Mars is actually moving in a more or less circular orbit. Elliptical, I guess, would be a better term for it. And so is the Earth. So why does it look like Mars is moving backwards? Well, the Earth is moving faster. So just like when you're on the highway and you're in a fast-moving car and you pass another car that's still moving, but it's not moving as fast as you are, it looks like that car, relative to you, is moving behind you. And so that's the same thing here. Basically, if Earth is moving faster, it can outpace Mars, and so it looks like Mars is falling back into the rearview mirror. Hopefully that makes sense. An old, outmoded idea that is useful for understanding the progress of astronomy through time. Thanks a lot for your attention. This has been another Smart Figure.
So the birth of modern astronomy started in the 1500s and 1600s. People started to propose new models and start to break apart some of the older ones. So we're going to talk about 5 noted scientists: Nicholas Copernicus, Tycho Brahe, Johannes Kepler, Galileo Galilei, and Sir Isaac Newton. Isaac Newton is the one who's going to put everything together into a model that can actually explain, not only explain the motions of the planets, but also why, or given a reason for it. So Nicholas Copernicus concluded the Earth was a planet. He proposed a heliocentric model. He constructed a model of the solar system that put the sun in the center, but he was still stuck on circles. He still used circular orbits for the planets. He still had to use epicycles to match data. But he didn't have to use epicycles to explain retrograde motion. So, that retrograde backwards motion that we see, that can be explained by, the heliocentric model. But he wasn't quite able to get the orbits right without adding epicycles. He published this in an incredibly dry book immediately before he died, thus saving himself from being investigated by the Catholic Church due to the secret trick of being dead at the time. But and it took a while for people to take notice of this. He was actually a monk. He was a monk, Polish monk. Now, this idea started to spread out. The church eventually banned it, but because part of that was because this was during the Protestant Reformation. A lot of these events were during the Protestant Reformation. So the Catholic Church was super defensive because of all the politics going on. People were fighting a war over religion, things like that. So they were getting super reactive about heresy and theological positions. Now, Tycho Brahe, who lived from 1546 to 1601, was a precise observer of the sky. He had the best data of anyone taken before the use of a telescope. He had the best data in the world. He tried to find stellar parallax. So one of the things is if the Earth is traveling around the sun, the positions of the stars we see should change over the year. Like if you hold your finger out and you look at it with one eye and switch to the other, your finger seems to move. That's parallax. And Tycho Brahe knew that if heliocentrism was true, you would see parallax. Now, parallax has been observed, but it wasn't observed until 1830 something, because it turns out stellar parallax is really, really tiny because stars are really, really far away. So he tried to find stellar parallax, and he didn't. So he didn't believe in this Copernican model of the solar system. So he proposed his own, but he did recognize some of the advantages. So he proposed his own even more bizarre model, where the sun and the moon orbited the Earth, and all the other planets orbited the sun in this bizarre hybrid model. And he was a real character. He got his nose cut off in a duel when he was young and had a fancy golden artificial nose for his silver artificial nose for special occasions. He got kicked out of several countries. Real character. And his assistant was Johannes Kepler. Johannes Kepler was the first person to really put together a real description of the motions of the planets that was a better model than any of the geocentric ones. And what he did was he was Tycho Brahe's assistant, but Tycho Brahe was really held on to his data very tightly. He was very reticent about sharing it, secretive. So when Brahe died, Johannes Kepler basically stole a bunch of data and ran off. And he had this idea of, he was a heliocentric, believed in heliocentrism, and had this idea about the planets rotating on spheres formed by nested platonic solids about the sun, which was completely wrong and bizarre. But he was able to, and the main thing that advantage he had over Tycho Brahe is he was actually good at math. He was a really good mathematician. So he was able to do some really excellent calculations over and figure out ways to extract information about the orbits of, well, he worked on Mars, the orbit of Mars from Tycho Brahe's observations and make what was essentially a detailed model of the orbit, compile a bunch of data points about the orbit of Mars, and then try and create models to predict the motion of Mars. And he got, he used a whole bunch of techniques, and he got stuck on a difference of what is 8 arc minutes. So that's 8/60ths of a degree in between his calculation and the observation. And that's what led to him throwing out circles and constant motion and grabbing onto the fact and putting together his 3 laws of planetary motion. But the orbits of the planets are elliptical, which she got to the shape of an ellipse in a horribly convoluted way as well. The planets revolve around the sun at varying speeds. He figured out a rule to explain how the speed varies. And there is a proportional relation between a planet's orbital period and its distance from the sun. So we'll go through these. So Johannes Kepler realized that the orbits of the planets weren't circles, they were ellipses. So this is Johannes Kepler. This is how you would draw an ellipse. An ellipse is like a stretched out circle. A circle is in fact a special case of an ellipse. And an ellipse has 2 what are called foci, or focuses. And those are special points in it. So Kepler's first law says the orbits of planets are ellipses, and the sun is at one of the focuses. Kepler's second law says the Earth travels faster. Well, it says that a planet will sweep out equal area. If you draw a line from the sun to a planet, it will sweep out equal areas in equal times throughout an orbit. That means when a planet is closer to the sun, it travels faster. When it's further from the sun, it travels slower. So Earth is traveling fastest when it's closest to the sun in January, and it travels slowest when it's furthest from the sun in July. Now for Earth, because the orbit is very close to circular, the difference isn't very big. But for something like a comet with an extremely elliptical orbit, that difference can be huge. And Kepler's third law describes the relationship between the size of the orbit of a planet and the time it takes to orbit the sun, which is the period squared is equal to the semi-major axis cubed. And then we have Galileo Galilei. Galileo supported the Copernican theory. However, he didn't manage to work with Kepler, even though Kepler had the solution, because he didn't like him, because Galileo was kind of a very abrasive person. Also, Galileo was Catholic and Kepler was Protestant. That was a big deal because this is during the middle of the 30 Years' War. He supported Copernican theory. He used experimental data. So he was the person to figure out, for example, that all objects in a gravity field fall with the same acceleration. And also figured out the concept of inertia. And he was the first person to construct a telescope and publish astronomical observations. So he wasn't the person who invented the telescope. He was the first person to actually use a telescope to observe the sky and publish. He made his own telescope, but he constructed an astronomical telescope in 1609 and made a number of observations that poked holes in the geocentric model of the universe. He observed 4 large moons of Jupiter, which indicated that things could orbit other things. They didn't have to orbit the Earth. He found that planets appeared as disks. They had some size, they weren't just points. And some of them had funny shapes, like Saturn had lumps, and he was able to observe a full set of phases of Venus. So if Venus orbited, if Venus orbited the Earth, it would not have a full set of phases. It would, because of the positioning of the sun and Venus, it would only have a partial set of phases. But if Venus orbited the sun, it would have a full set. And his observations of the size of Venus and its phases corresponded with what you would expect for Venus orbiting the sun. He observed features on the moon showing it wasn't a perfect sphere, poking holes in this, perfection, and he observed sunspots. Again, showing that the sun had features and wasn't just a ball. So this is Galileo. This is a Galilean telescope. Very simple telescope, 2 lenses. Because this is shortly after the telescope had been invented. So he discovered that Venus had phases like Earth's moon, as opposed to what it would have if it was, in a geocentric model. So Venus confirms the Copernican model, is one of the things that Galileo.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. This time we're going to take a look at one of the major insights in the history of science, the realization that the Earth is not at the center of the universe. So the prevailing idea until Copernicus showed up was the Ptolemaic system. Ptolemaic has that silent P in front of it, by the way. The Ptolemaic system has the Earth at the center of the universe, and basically everything else in the universe orbits around the Earth because we are so doggone important. So the moon orbits around the Earth, Mercury orbits around the Earth, Venus orbits around the Earth, the sun orbits around the Earth, Mars, Jupiter, Saturn, they're all orbiting around the Earth. But Galileo used a telescope to show another idea was actually correct, and that the Ptolemaic idea was not correct. So here are 2 slides that contrast what Galileo was looking for. So if the Ptolemaic system was correct, the planet Venus orbits the Earth, and so it comes in from the right here, and it's also following its epicycle, and then it moves out of sight off towards the left here along its deferent. So what we would expect to see as Venus reflects the sun's light is that when Venus is directly between Earth and the sun, it would look very dark to us. And so it's going to be smallest, furthest away from the Earth, and darkest at that point. And then Venus will get closer to us, and it'll get these sorts of crescents where part of it is illuminated and part of it is not. And it'll be largest, of course, when it's in these 2 crescent phases here. Now that's in contrast to the Copernican system, and the Copernican system basically has the Earth and Venus both as planets orbiting the sun. And so basically here, Venus is going to be at its darkest when it's closest to us. That's the opposite of what we would expect with the Ptolemaic system. And then as it moves along its orbit, when it's furthest away from us, a maximum amount of its area will be reflecting sunlight. And then, of course, it'll move along its orbit and return to its original position. So those 2 different models, or those 2 different systems, make very different predictions about what we would observe if we were looking at Venus and looking at the phases of Venus. So what did Galileo actually see when he looked through that telescope? Here's the data. Here's what he actually observed. So he observed Venus has this sort of crescent phase that you see down here on the lower left, and then basically that it gets smaller as it gets more and more round. It reaches maximum round area, so maximum sun coverage, when it's furthest away from us. So in other words, the Ptolemaic system has got to be wrong, and the Copernican system has got to be right. So ever since Galileo made that critical observation through his telescope, we basically have realized that the Earth is not at the center of our solar system. Instead, we are but one planet orbiting a star, and there are many other planets like us. And of course, that's just one star in our galaxy, and our galaxy is just one galaxy in the universe. Thanks very much for your attention. This has been another Smart Figure.
And because Galileo was a very abrasive individual and presented his ideas in a manner that was, rude, he put the words of the Pope in a character named Simplicio, implying that, geocentric people who held the geocentric position were simpletons. He got tried for heresy by the Inquisition and put on house arrest for the last 10 years of his life. He was finally officially vindicated in 1992 because the Catholic Church moves slow. I mean, his book was removed from the banned books list in like the 1830 or something. So they're just slow. And then here we have Sir Isaac Newton. Sir Isaac Newton took the work of Galileo and Kepler and put it together with his own ideas about gravity, and by using his ideas for understanding of motion, his three laws of motion, and the law of universal gravitation, his explanation for gravity, he was able to show that and prove that the force of gravity, where gravity is every object with mass is attracted to every other object with mass, with a force proportional to the mass is multiplied together, divided by the distance between them squared. That's Newton's law of universal gravitation, and combining that with his second law of motion, that acceleration of an object is equal to the force of that on that object divided by the mass. He was able to use those two concepts and derive Kepler's laws from it. So he was able to generate Kepler's laws from first principles, kind of. Showing that with the tendency of a planet to remain in straight line, the force of gravity with the tendency of a planet to remain in straight line motion results in elliptical orbits as discovered by Kepler. And the way he proved it is very confusing. So he went on and invented calculus to make the math easier. It really does make the math easier. This happens to be something where, this is precisely what calculus was invented for. It does make solving this sort of problem a whole lot easier. But the basic idea is that when something is orbiting, it's falling towards the larger object, but it's moving sideways fast enough that it misses. So if you want to orbit the Earth, the trick is to move fast enough sideways when you fall down that you miss the ground. So you get a curved motion because you're being pulled towards the sun, and then you move a little, and you're being pulled towards the sun in a slightly different direction, and eventually you end up going around in a circle or an ellipse, because it doesn't have to be a perfect circle. Well, we still have time, so let's talk about patterns in the night sky that we can see. So if we look at the sky, we see constellations. What we do is we see a whole bunch of essentially randomly distributed dots. But humans are pattern recognition machines, so we draw pictures in the random dots. So constellations are configurations of stars named generally in honor of mythological characters, great heroes, things like that. We draw pictures of the sky, we name them after things. Everybody does this. So every culture had its own set of constellations. The modern constellations that get used are primarily the Greek ones, because just Western science is derived from Greek science. So the modern use of constellations in astronomy, however, is not so much let's draw pretty pictures in the sky, which is a perfectly positive and viable thing to do, but constellations in modern astronomy are used as a way to organize the sky. Because it turns out, if you say the location of something with just, it's so many degrees east and so many degrees north, that's hard to intuit. But if you say it's in Orion, then that's a place. So it works like states, kind of. So the 88 constellations are recognized. They divide the sky up into units like state boundaries in the US. And the brightest stars in a constellation are identified in order of their brightness by the letters of the Greek alphabet. So you'd have Orion Alpha, Orion Beta, Orion Gamma, and so on, from brightest to dimmest. So this, gives you something like, this is the celestial sphere. You can think of it as if the sky were a big dome on which all the stars were on. You can describe the locations of various things on this celestial sphere, and you can set up a system like latitude and longitude for the stars. So here are some example constellations. Here's Orion, here's Pegasus, here's the Big Dipper, here's Gemini, the Southern Cross is down here. The North Celestial Pole, there happens to be a star there at the moment, which is Polaris. But it's not always going to be there because the Earth wobbles. So it rotates, the position of the North Celestial Pole rotates around the sky every 26,000 years. This?
Like those stars, they're not there right now. They can be anywhere on here.
Well, this is where these various stars are located if you look at the sky. And it's as if this big ball is rotating around the Earth.
It's not stars. Just
These are some specific stars, like
Yeah,
the
but
stars of the Southern Cross.
like the ball is rotating, but the stars are.
Well, what's actually happening is the stars aren't moving and the Earth is rotating. So your point of view is rotating.
Okay.
But they don't move relative to each other.
Okay.
But where the North Pole points is called the North Celestial Pole. It turns out over centuries that moves.
Okay.
So the celestial sphere, stars appear to be fixed on a big spherical shell around the Earth. That's not actually the case. They're distributed over, hundreds or thousands of light years around us in the galaxy. But this conceit of a spherical shell around the Earth is useful for describing where things are located in the sky. I can say, where something is, where to point my telescope, kind of thing, by using this celestial sphere. So measurements using the celestial sphere, we measure along the horizon, we measure in degrees clockwise from due north. So if you're standing on looking at the sky, if you want to figure out where you're pointing, you'd measure starting facing it due north, and then you'd rotate clockwise. So rotating towards the east, and however many degrees you're pointing, that's the direction. And then how high above the horizon you are. That's how you tell where something is from your point of view. There's also celestial latitude and longitude, which is fixed relative to the stars. But if you want to describe where you're observing something from where you're sitting on Earth, you describe it with the altitude and the direction. So the altitude is how many degrees up you have to look, and the direction is what direction you have to face, basically. And you measure that in degrees starting from due north. So directly overhead will be an altitude of 90 degrees. At the horizon will be 0. Due north is 90 degrees. Due north is 0 degrees. East is 90 degrees. South is 180. West is 270. Now, the Earth is moving around the sun, and it's primarily moving in two different ways. First of all, is spinning. It is rotating about its axis. That is what gives us a day. It's also what causes the stars to move across the sky, because the Earth is rotating. The mean solar day, or the average day we observe by looking at the sun, is the time interval from when the sun is directly overhead to the next time the sun is directly overhead. So from noon to noon. That's pretty much 24 hours. That's where we get the 24-hour day. But there is also the sidereal day. If we look at the stars and see from when a star is directly overhead to the next time that star is directly overhead, we'll find that it's a slightly different amount of time. It's a little bit less. It's 23 hours and 56 minutes and 4 seconds. And that is because every day where we rotate, we also travel a little bit around the sun. So we have to rotate a little bit further for the sun to be back directly overhead. And that causes the difference between what's the solar day, the day with respect to the sun, and the sidereal day, the day with respect to the stars. So here, this is slightly exaggerated, but the idea is that in one day, for a sidereal day, we've rotated back around, so a distant star is in the same position. But because we've traveled a little bit around the sun, we have to rotate a little bit more, 4 minutes more, for the sun to be back overhead. And that difference is not huge because it's a little bit less than 1 degree. So it's only about 4 minutes. If we were traveling around the sun more slowly, it would be, if we traveled around the sun more, if we were traveling around the sun faster, it would be a bigger difference. So there's a similar effect with the moon. As the moon travels around the Earth, its phases are tied to its relative position to the sun, but there's also a sidereal moon thing, and that effect is bigger because the moon takes a longer time to travel once around the Earth than the Earth takes to rotate. So, the two primary motions. It rotates around its axis, it spins, and it revolves around the sun. The Earth's orbit is elliptical around the sun. It's closest to the sun in January and furthest from the sun in July. The distance from the sun has very little effect on the weather or the temperature.
I was gonna say like.
So it turns out the effect that causes the seasons is that the Earth's rotation is tilted with respect to the sun. Which is why when it's summer here in the northern hemisphere, it's winter in the southern hemisphere. And the other way around. When it's winter here in the northern hemisphere, it's summer in the southern hemisphere. So that's what causes the seasons. So it's, because the Earth is spinning, but the axis isn't pointing in the same, perfectly at right angles to its orbit around the sun, it's tilted by 23.5 degrees. That means one hemisphere is pointed more toward, gets more sun. And the other hemisphere gets less sun. Because it's, one hemisphere is basically pointed more towards the sun and the other one's pointed away. So during the summer, the northern hemisphere is pointed towards the sun, and the southern hemisphere is pointed away. And that has a much bigger effect than the difference in distance, which is very small. Because the Earth's orbit is almost a perfect circle. And that tilt is what causes what's called the ecliptic, which is the apparent annual path of the sun against the backdrop of the celestial sphere. So you may, that's why that tilt is what leads to days in the summer being longer and days in the winter being shorter. and why the sun is higher in the sky in the summer and lower in the sky in the winter, which is the main effect that causes it to be warmer in the summer and cooler in the winter. And the Earth orbits with the sun around the galactic center every 23 million years. So there is, in fact, an orbit around the center of the galaxy. It just takes 23 million years to occur. So it's not very fast.
So, will they have it come in?
Hmm?
Will they have it come in?
Well, so that's our whole galaxy is rotating. I mean, the Earth is older than 230 million years, but humans aren't. But yes, our whole galaxy is rotating around, well, the supermassive black hole in the center of it. So the ecliptic is sort of, if you can project the equator out, but the ecliptic is really just the plane that corresponds to the solar system. The solar system is basically flat. All the planets, the sun, the moon are all pretty much in the same flat plane. The moon is tilted about 5 degrees from it, but yeah. So there's a plane of the equator, and then there's the plane of the ecliptic. And they differ by 23.5 degrees because the Earth is tilted. But the ecliptic, that line, the plane of the ecliptic, has been considered important for thousands of years because it's where the sun ends up. It's also where all the other planets end up. And so that's where your zodiac signs are. The zodiac signs are the constellations along the ecliptic. And they're actually older than most of the other constellations. A lot of them are holdovers from Babylonian stuff. Let's see, what time is it? It is, oh, it is, no, it's too, we still have a bit of it more time. So I'm just going to keep going. I have old announcements in here, sorry about that. Yeah, because we're here till just before 3, so we're done. Now, so that's how the Earth moves around the sun. And additionally, the moon orbits the Earth. Its orbit is elliptical because all orbits are elliptical, pretty much. And there are, we can describe 2 months like we can describe 2 days. There is the synodic month, which is the cycle of the moon through its phases every 29.5 days. That's the month we think of as a month. Now, if you look at the moon, that's the cycle of phases. It's the thing we can observe. This was the basis of the first Roman calendar. It's the basis of a lot of calendars. It's the apparent period of the moon's revolution around the Earth. But it turns out we can also look at how the moon moves across the backdrop of stars. And that is the sidereal month. And the period of, that's the true period of revolution of the moon around the Earth. And that is a couple of days shorter. It's 27.3 days. And the reason it's shorter than the synodic month is the same reason the sidereal day is shorter than the solar day. But it's a bigger effect because the month is longer. So you move further around the sun, so you have more to catch up. So the difference in the 2 days between the synodic and sidereal cycles, that's due to the Earth-Moon system also moving in orbit around the sun. Now, the moon has become what is called tidally locked to the Earth. That means the same side of the moon is always facing the Earth. So if you look at the moon up in the sky, you're always seeing the same side of the moon. There's a near side of the moon and a far side of the moon. The far side of the moon was not observed until the 50s, when the Russians were able to send a satellite behind the moon to take pictures. The period of rotation around its axis and its revolution around the Earth are the same. So basically, it's rotating around the Earth at the same rate that it's It's revolving around the Earth at the same rate that it is rotating about its axis, so the same side always faces the Earth. And this is something that happens over time. There are certain forces that slow down rotation so that you end up with one side always facing the other object. The moon is affecting the Earth's rotation in the same way. It's actually slowing down the rotation of the Earth over long periods of time. The effect is tiny, but it is an effect that is happening. But it does cause the same lunar hemisphere to always face the Earth. So we're always seeing the same side of the moon. Any apparent rotation is just the shadow of the moon on itself passing over it from the phases. So here we have the difference between a sidereal month and a synodic month. A sidereal month, you get to here, and then takes another couple of days to have the moon back in between the Earth and the sun. Because the Earth and the moon travel around the sun over the 27 days or so. That it takes the moon to rotate once around the Earth, and then it needs to do another couple of days. So when we look at the moon, we see phases. So when viewed from above the North Pole, the moon appears to orbit the Earth, and it orbits the Earth in a counterclockwise eastward direction. And the relative positions of the sun, Earth, and moon constantly change. And the lunar phases are a consequence of the moon moving around the Earth and what portions of the moon are illuminated by the sun. So the relative positions of the sun, the Earth, and the moon. Because, the lit up portion of the moon is just sunlight being reflected off the surface of the moon. So the phases of the moon are caused by, the lit portion is just the side that is facing the sun. The dark portion is the side that's facing away from the sun, so it's in its own shadow. The moon is blocking the light from the sun.
I always thought that it just showed up like that.
So if you have a light, so it's basically what's going on is if you had like a light source over here, so all the light is coming from over here, and you have a ball. It's only going to light up one side of that. The side of it that's lit up changes over the month as it orbits around the sun, as it orbits around the Earth, and that changes what portion of it we see illuminated. Half of it is always illuminated. That half changes over a month. So the day, if you were on the moon, the day you would experience would last a month. The sun would rise, set, and rise again over the period of a month. And that causes the phases of the moon. So it's not caused by the shadow of the Earth on the moon or anything like that. It's caused by the shadow. It's actually caused by the shadow of the moon on itself. The shadow of the Earth on the moon is a lunar eclipse, which we will get to. So here is a short video about the phases of the moon.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe how and why the moon changes phases. When we look up in the night sky and we see something like this, what are we to make of it? What does it mean that the moon has this sort of crescent shape? Does this mean that the moon is actually a crescent and that somebody could, say, sit on that lower edge? Absolutely not. What you're looking at here is the moon as it always is, which is essentially a sphere, except different portions of the moon are lit up. And right now, in this picture, most of the moon is in shadow. But what's casting that shadow? A misconception that many students have is that that shadow is being cast by the Earth on the moon. That is absolutely not the case with the phases of the moon. That's the case with an eclipse. We talk about eclipses in a different portion of the textbook and in a different Smart Figure. So for the moment, set this aside. The phases of the moon have nothing to do with the Earth's shadow. Instead, what they have to do with is the moon's shadow. The moon is a solid object, it blocks light from the sun, and if you're looking at the shadow side of the moon, then the other side of the moon is the one that's lit by the sun. One problem here is the misnomer, the dark side of the moon. The dark side of the moon is dark for only half the time, and the side of the moon that faces Earth is dark for half the time. So really, the dark side of the moon should be called the far side of the moon. Anyhow, if you are standing on Earth and it's high noon and the sun's rays are coming directly down from above, then the moon, if it's directly above you at that point, will appear mostly in shadow. That'll be called the new moon, and it's illustrated down here. On the other hand, if the moon is moving into a position where we can see more and more of the sunlit portion of the moon, that is called a waxing moon. So if you're standing in this position here, basically at sunset, where the sun is setting to the west and the land to the east of you is already in shadow and darkness and night, then you will look up into the night sky and see the moon in this sort of a position here. So this is called a first quarter moon. And notice that the western half of the moon is lit because that's where the sun is, in the west. As more and more of the moon is flooded by light over the course of the month, we say it is waxing. It's growing in terms of the amount of the sunlit portion. When it's more sunlit than not, we call it a gibbous moon. Eventually, it gets to be on the opposite side of the planet from the sun, and so we can see pretty much all of its surface lit by the sun's rays. That's called a full moon, and that's going to be best viewed at night. If you're on the opposite side of the planet during a full moon, you're not going to be able to see it because it's not going to be in the sky. When we rotate around to this position here, we can see that we're at sunrise, where the land to the east of us is sunlit, and the land to the west of us is still dark in night. And if we look up in the night sky, we're going to see, again, a gibbous or a third quarter or a crescent moon, but in this case, it's not waxing, it's waning. So more and more of the moon's surface is getting shadowed as opposed to being lit by the sun. And notice also that it is now the eastern half of the moon that's being lit. Here's a comparison of how that would look in the night sky. If you're looking at the same position over time, you would see basically that during sunrise, the eastern half of the moon would be lit, and so therefore this would be waning. And during sunset, if you see the western half of the moon lit, that's an indication that the phase of the moon is waxing. So that's a waxing crescent moon. Okay, let's go ahead and test out your knowledge here. Here we're looking down on Earth from above the North Pole, and the orbit of the moon is traced out with this circle. The incoming rays of light from the sun are shown by the yellow arrows on the right. Where would this phase of the moon fit in on this circle? Assume that the left side of the picture is east and the right side of the picture is west. So what you're looking at here is that the eastern half is lit and the moon is about half lit, so that's going to be a third quarter moon, and it's going to fit in somewhere about right here. What about this one? Well, that's obviously a full moon, so that's a pretty easy one. That's going to fit in over here, where the sunlit portion of the moon is the one that we can see from Earth's surface. How about this one? This is a crescent moon, and again, assume the eastern half is lit, so that makes it fit in about right here. And finally, we have a gibbous moon, which has the eastern half lit, so that's going to fit in about right here. Okay, I hope you got those right. Thanks a lot for your attention. This has been another Smart Figure.
Oh, made more progress than I expected. Okay, let's talk about eclipses. We are running a little ahead of schedule, but it's probably a good thing. Just means other things. So eclipses are shadow effects. They're the shadow of one thing on another. And they were first understood by the early Greeks. And there's two basic types of eclipses. There are solar eclipses, where which is the shadow of the moon on the Earth, because the moon is in between the sun and the Earth. They can only occur during the new moon phase, because that's when the moon is in between the sun and the Earth. And then there are lunar eclipses, which is the shadow of the Earth on the moon. And is actually how Aristotle was able to determine that the Earth was round. So this is a solar eclipse. Solar eclipse, we have the sun coming from over here, the moon throws a shadow on the Earth, and there's a small area on the Earth that is in shadow. And because, due to a current cosmic coincidence, the moon in our sky is pretty much the same size as the sun in our sky, which was not always the case because the moon is steadily moving further away from the Earth as its rotation slows down, or speeds up as its orbit changes over time. But there's a cosmic coincidence right now in history. The moon is almost exactly the same size as the sun, so we get some of the most dramatic possible eclipses. None of the other planets have eclipses as good as us, because their moons are much smaller than the sun in the sky, or much bigger. But this is the shadow of the moon on the Earth, and when you're in that shadow, it's super dramatic. There was that big eclipse recently, a few years ago, that was very impressive, and we got 95% coverage of the sun around here. So this is an eclipse. You can see the shadow of the moon on the Earth, and in the very center, the darkest spot there, that's where there's a total eclipse. And because the orbits of the Earth and the moon are not perfectly circular, they're both elliptical. Sometimes you can have what's called an annular eclipse, where the sun is closer and the moon is further away, and the moon ends up smaller in the sky than the sun, so you get a ring around the outside. Now, a lunar eclipse is when the moon moves into the shadow of Earth. So for any eclipse to take place, the moon has to be in the plane of the ecliptic. And because the moon's orbit is tilted about 5 degrees from the plane of the ecliptic, it turns out there's only about 2 times a year that are eclipse season. And eclipse season happens about twice a year. One in I think it's like in April and October, roughly. Eclipse season, the moon is at the right, is close enough to the ecliptic for about a month. It gives time for usually 1 solar eclipse and 1 lunar eclipse. Solar eclipses are much harder to see because they affect a much smaller portion of the Earth, because there's that line across the Earth where you can see the actual solar eclipse. Because the Earth is big and the shadow of the moon on the Earth is relatively small. But lunar eclipses are much easier to see. Because you could see the shadow of the Earth on the moon from anywhere on the night side of the Earth. Also, they last a lot longer. They last for a few hours. So during most of the time, new moon and full moon, the moon is either above or below the ecliptic. No eclipse can take place. If the moon's orbit was level with the orbit of the Earth, we'd have an eclipse every month. We'd have a solar eclipse and a lunar eclipse every month. And the usual number of eclipses, because of that angle, is about 4 per year. So for a lunar eclipse, the Earth is between the sun and the moon, and the shadow of the Earth falls on the moon. And because the Earth is much bigger than the moon, its shadow is subsequently bigger. And so you get, if the moon is, as the moon passes in, you get a curved arc as it passes in. And then when it's fully within the shadow, the only light you get is light that has been scattered around at the edge of the earth, which is affected more for long wavelengths for various reasons. So the moon turns red. So if you've heard of a so-called blood moon, that's a lunar eclipse. So here is a short video about eclipses.
Hello there and welcome back for another Smart Figure. After watching this video, you should be able to distinguish between the two kinds of eclipses, solar and lunar. Here are a series of photos showing the development of a solar eclipse, the maximum solar eclipse where the sun is blotted out by the moon, and then the decline of the eclipse again back towards a normal look at the sun. A solar eclipse is when the sun is eclipsed by the moon. And what this means is that the moon moves between Earth and the sun. And so the shadow of the moon is projected onto the Earth's surface. The path of the total solar eclipse is where we have what's called the umbra, basically the maximum shadow, nothing but shadow. And the size of the moon is almost about the same size as the sun. And so we basically see a black circle in the sky, and then that's surrounded by emanating rays of the sun. There's a wider area surrounding the umbra called the penumbra, and that's where there is going to be a partial solar eclipse. So if you're standing in the penumbra zone, you will see the sun partially obscured by the moon. Now there's also a lunar eclipse, and this is when the moon is eclipsed. Rather than the moon getting in between the Earth and the sun, the Earth is getting in between the sun and the moon. And so the shadow of the Earth is actually cast onto the moon itself, again with this sort of umbra-penumbra relationship. And that puts the moon in shadow. Now this is not by any means the same thing as the phases of the moon, where we see a new moon, a waxing crescent moon, a first quarter moon, a gibbous moon that's waxing, and so on. Here what we're seeing is something that transpires in a matter of hours where the moon passes through Earth's shadow. The regular phases of the moon are caused by the moon's own shadow, but this is the Earth's shadow instead. You can see that the boundary between shadow and not shadow is much more diffuse than in the case of the phases of the moon. That's one way to tell the two apart. Okay, quick quiz here. See if you can spot whether this is a solar eclipse or a lunar eclipse and tell me why. All right, so the sun's on the left, and then we've got the two objects on the right, one of which is the moon and one is the Earth. Obviously, the Earth is the bigger of the two. Here, the moon is between the Earth and the sun, and the moon is casting its shadow on the Earth. So this would be an example where the people in the umbra are basically going to not be able to see the sun. The moon's going to be blocking their view of the sun. So the sun will be eclipsed. Therefore, this is a solar, not a lunar eclipse. Thanks a lot for your attention. This has been another Smart Figure.
So that is where we're going to stop for today. That actually covered pretty much all of chapter 21. I will go over a bit of that next time, and also that bit we missed out from the first meeting, because we're now ahead of schedule. So, okay. Let me okay.